Western University and also from Nanjing University of Information Science and Technology. So this work is about, from the title, is a new generalized error path algorithm for model selection. So generally, it's a work about model selection. So it's a classical and important topic. This work is joint work with Professor Charles Lin from Western University, and this slide gives the outline of this presentation, and we will first introduce the background. As we all know, model selection with cross-validation is very popular in the machine learning, and normally we use the k-fold cross-validation for the model selection. And from this picture, give the schematic diagram k-fold cross-validation, and we partition the validation set into k paths, and each time we select one path for the validation set and select other paths for the training data set, and run k times over, and we compute the average cross-validation errors. So if we select one sample as the validation set, so this is called leave one out cross-validation, and if we randomly select some examples, randomly select some samples as the validation set and others for the training data set, so this is called repeatedly random subsampling procedures. No matter this all kinds of cross-validation methods also need to work with a group of candidate values or parameters. The most popular strategy is grid searching. This is an example for grid searching for supervector machine. The regularization parameter C and also supervector machine is searched on 18 grid linearly spaced in this region. This is used in this paper. And there are also other searching strategies like manual search and random search. They are usually used in the deep learning. No matter grid searching and manual searching and random searching, they also have a common. They have a common weakness. The weakness is that they only consider finite candidates due to the limited computing resources. But as we all know, the ultimate goal of model selection is to find the model with the minimum cross-validation error in the whole region, in the whole parameter space. So we introduce a novel method called solution path. This gives a picture to show the solution path of the Lasso with respect to the regularization parameter. So from this picture, we can show that all solutions of the Lasso can be computed by a finite number of representative solutions, as shown the dotted line. So generally, we can compute all solutions based on a finite number of solutions. So this is interesting work, and there are also a lot of such works about solution paths on a lot of kinds of supervector machine, and Lasso and kernel quantile regression and other general problems. And this solution path maybe give the exact solutions or other approximate solutions. And however, solution paths do not guarantee to find the model with the minimum cross-validation, because they do not correspond to the error path. They just a solution path. But the only work on the cross-validation with global search is the work of Yang and Ong in 2011. Their method is based on the solution path of Hasty et al. 2004 and Ong et al. 2010. This work on state classification and the work on standard error function of binary classification. Overall, this method is limited to the two solution path algorithms and error functions of binary classification. So our motivation is to design a generalized error path algorithm. It can cooperate more general error functions, and not only for the binary loss function of the binary classification. And we also want to work with more general solution paths, not like in this work, only in the solution paths of ST and OM, their work. So most importantly, we want to obtain the minimum cross-validation error directly for a large variety of error functions and the solution path algorithms. So this is our motivation. And the next we will introduce our proposed generalized error path algorithm. This is a picture gives the roadmap to the error path. And the main idea is that the piecewise linearity of solution paths leads to the piecewise linearity of the model function. And based on the piecewise linearity of the model function, we can prove that the error path may be piecewise linear, or piecewise constant, or piecewise nonlinear. So this is the basic idea. Firstly, we will introduce the piecewise linearity of the solution path. This is the definition for the piecewise linearity of the solution path. And from the definition, suppose alpha lambda is returned by a solution path like in this picture. This is a solution, this is a solution, this is a solution, and this is the parameter lambda. So solution alpha lambda is called piecewise linear as a function of lambda if existing sequence of contiguous interval like such this is interval, and the corresponding and there is a sequence of vectors beta, and this is beta. Vector beta, and the solutions alpha lambda is given exactly or approximately by this linear function. Like in this interval, all solutions can be computed by this linear function. So this is called the piecewise linearity of the solution path. And we also find that the representative solution path algorithm, most of solution paths, they are all piecewise linear. So this is given table to show that the solution paths on a lot of kinds of supervector machine, Lasso, kernel compile regularization, and other learning programs, their solution paths are piecewise linear. And based on the piecewise linearity of the solution path, we will show that the model function are also piecewise linear. Before show this conclusion, we first give an assumption that our model function is with a linear representation like this function, and we also give some support, for example, on the support vector machine and the Lasso and the kernel compile regularization. Their model is also like this linear representation. So based on the solution path and the model is the linear representation, and we will give a lemma to show that the model function is also piecewise linear. They can compute this linear function in a subinterval. So this is also examples that for the support vector machine and the Lasso and the kernel compile regularization, there's model function also like compute. They are also piecewise linear, and so based on the piecewise linearity of the model function, we next to prove that the error path on the entire intervals could be piecewise quadratic, and could be piecewise linear or piecewise constant on common error functions for regression and the binary classification. This picture gives an example, and this red line is an example of the piecewise error path is piecewise constant, and this blue line is an example of that the error path is piecewise linear, and this This linear is an example of the error path is piecewise quadratic. So we first consider the first case that piecewise error path is piecewise quadratic. So we consider the square error function for duration, and y here is a true value of the input, and the y hat is the predicted value of the input. So we want to compute the mean square error. If given a subinterval based on the piecewise linearity of the mode function, we can compute the mean square error function. So this mean square error function can be computed as this formulation, and it's easy to find that the formulation is a quadratic function of the lambda. So we conclude that the error path on the mean square error is piecewise quadratic in the whole region. So this is the first case, and the next case is that the error path may be piecewise linear. We consider the absolute error function, and this is an absolute error function, and similarly, y here is a true value of the input, and y hat is the predicted value of the input. This is the predicted function, and we firstly give a partition on the validation, which based on the sign of this function. That is the y tiered minus to fx tiered, and the partition have two parts, and one part is corresponds to the labels have the positive sign like this, and the other part corresponds to the labels having the negative sign. So based on the partition, we define a invariant region of lambda. This invariant region share a same partition like defined in this formulation. And now we are interested in the invariant region. So what kind of invariant region? This theorem tells us that the invariant region is a convex set, and its closure is a non-trivial interval region. So this means that this invariant region is an interval and not a single point. So based on this invariant region, we compute the mean absolute error at this function, and it's easy to find that the mean absolute error function is linear, and we conclude that error on the mean absolute error is piecewise linear. And next, we consider the case of piecewise constant, and we consider standard loss function as this function, and we have also defined a partition on the validation set as like this. It's based on the sign of the predicted label of the predicted label. So we also divide a invariant region of lambda, and this share a same partition, and also we give a theorem to show that the invariant region is also an interval and not a single point. So next we show that the error rate is a piecewise constant because of this function. And similarly, we can also prove that the error path on weighted error rate or precision or recall or F measure, they are also piecewise constant. So based on various error paths, we want to compute the various error paths. We define a two-table, like I is an interval and P is a set of parameters to describe quadratic or linear or constant function, and this is how to do these parameters. So next we give the algorithm. This algorithm to first there is an inner loop to compute the error path for the sub-interval based on the piecewise linearity of the mode function, and finally we repeat this procedure on all intervals to give the error path on the whole region. We also can compute for cross-validation error, just the average k error path. So it can be implemented by a simple match procedure. Finally, we give our experiment results, and this is the data set in our experiment. The first file is the data set for binary classification, and the last 5 is the data set for the regularization. And the first result shows that we can find our method can find the minimum cross-validation error compared to the query search, manual search, and the random search. And the second table to show that our algorithm can give the better average errors on the testing set over 10 tries compared with the query search, manual search, random search. So in conclusion, we propose a new generalized error path algorithm, and it can incorporate more general error functions, and it can work with more general solution path algorithms. And most importantly, it can obtain minimum cross-validation error directly for a large variety of error functions and the solution path algorithms. In the paper, we also discuss our algorithms on the other learning problems such like ordinal regression, multiple classification, or ranking. And if the error path on this learning problems is available, our general error path can work on these problems. Finally, we want to extend our work to other loss functions such like error on the curve and other loss functions. So that's all. Thanks for your attention.
So in your experiments, you compare to grid search, random search, but obviously these have like how many times you try, you have the parameters. So the best thing to do is compare it in terms of total computation time. What is the best validation error you get? So if you go back to your experiments table, how many